Doris argues that architects have a responsibility to play in solving them. I don't think Doris has much tolerance for ill-considered design and unsustainable practices that only worsen our current predicaments. In her presentation, Doris will discuss some of her projects and their underlying philosophies. Afterwards, not during the presentation, after the presentation, there will be time for questions from you, technology willing. So now I'll hand it over to Doris Sung in Los Angeles.
Yeah, thank you very much. Thank you, John, and thank you, Brent. I'm super happy to be here, or actually there. It's kind of weird that I'm the only one who's remote, but it's a normal thing for us here in the US. I titled this lecture Moving Targets for probably obvious reasons, and I break it down into different parts. It's a way to bring my work current and relative to things that are going on, and I actually think they do strongly relate to each other. What I'm going to do is I also tried to put the lecture together so that I preempt some of the questions that many people will have. I talk about my background a little. I talk about the different facets of my work, as well as, like I said, its relativeness to today. But I also try to show that the work is very purpose-driven and something that I'm very passionate about, and so much that I actually left the typical architecture profession or practice to do more research. So I'm going to start. Sorry, give me a second here because I now need to find the clicker. Is it working? Yes. So when I first went to college, I actually had no idea. Again, I did not know that I wanted to be an architect. I didn't even know exactly what they did except build buildings. At that time, I actually wanted to be an artist. I wanted to major in visual arts. And my parents said, absolutely not. You know what I mean? You're going to have to make a living for yourself. Do not pursue that. What I did instead was I actually decided to major in biology. And that was the second love of mine. I went into biology thinking that the entire time I'd be in school, I would then also take art classes at the same time. I'm trying to click this clicker and I'm not getting any action. Are the things forwarding for you all?
Yes, they're clicking.
Okay, I'm frozen on my screen again, so I only see like the second slide. I don't know how to.
Just
I don't know what slide is up. So
I'm just going to send you the slides on the clicker as well, and you'll be able to see it on your phone.
Oh, that would be good. Yeah. Sorry about that. There's always like technical problems, isn't there? Oh, I kind of see something. Okay. I see something. Okay, I guess we're at the start again. So I'm going to try to forward. This is some artwork that I did in school. So what I did was all the way through undergraduate and graduate school, I always took a visual art course. And I say this, and it's significant because a lot of people ask me how I came up with my aesthetic or understanding of materiality. And I think it started very early and not intentionally. I just did it because I loved it. But I ended up majoring in biology and got very infatuated with animals, cell biology, all the way to animal behavior. Before I actually became an architecture major. And part of it was because my advisor in college said to me, it's like, oh, instead of applying to medical school as a biology major, it would set you apart if you actually had a different major. So I thought, oh yeah, that's a great idea. And decided to do architecture thinking, well, that would be really cool. Nobody would do that. But I did end up pursuing architecture after I graduated because I started to enjoy it a lot. And really started to look at that division between the organic and the inorganic. And so you see in this image, there's this kind of remnants of things that were alive and its structure and enclosure of holding it together. Then I actually started to extend that a little further so that it extended into this idea of sensation. And through these inanimate objects and inanimate material, how can we extend that sensation through it? So you see through the prosthetic device, as well as the extended fingers by Rebecca Horn on the right. The more you use these things, the more you actually can feel sensation, and you can actually touch and feel things through it. So you can feel the size of it, the texture, all these types of things. And I thought, well, if you can do that with inanimate objects, why can't we do this with architecture? Why can't architecture do a lot more than what we expect? Why does it have to be static? Why can't it be dynamic? And why can't it feel sensation? So, sorry, one second. Mina? So I started building these artifacts that were inanimate, but actually became dynamic. And so I did this all the way through graduate school, building these things that incorporated the body. So this is a lock that you see that used my face to unlock the device. I started making things that were bigger and bigger, and there were always a connection back to either the human body, biology, and how we can manifest it in built things and detailing. And so during that time, I actually practiced as an architect. I had a firm. I worked for other firms too. I don't show a lot of that work, not because I'm not proud of it, but because there's a really big change for me. When I started reading this book, Field Notes for Catastrophe, by Elizabeth Colbert, it really struck a chord in me, because I thought, wow, we are really headed to a climate crisis, and that it is truly a catastrophe. And why aren't we doing anything about this in architecture? And this was about in the early 2000 years. And so I started really almost even losing sleep over it. So then I extended this idea. It's like, okay, if climate change is actually happening, why isn't the envelope of the building at least, or why isn't the building responding to these changes? Why can't we look at the envelope, and so that as the climate change, not only in a daily basis and an hourly basis, but also on a yearly basis and in a decade basis, so that our buildings were prepared for these kind of catastrophes eventually. And then I tried to look more carefully at why are our buildings falling down during earthquakes or hurricanes or floods and all these different things, and what were the buildings that were actually truly smart. And then I started to look historically into things like these igloos, where I'm sure you've seen this before. The shape of it is structurally sound, being this big dome, and the fact that it's round, and at the top the winds can actually blow and move over and around them without uprooting the system. The entire thing can be built locally. It didn't require a lot of equipment, and the tiny air bubbles inside the ice was very, very good at insulation. On the inside, when you have the fires going, the fires themselves would actually melt the inside surface and seal all the cracks. So there's something very smart about living with this very renewable energy source. Also, in yurts, the same thing happened. The portability for the nomadic life, the fact that they were made out of animal skins or felt from the furs, and that they can actually breathe. They're waterproof. They do all these types of things that our buildings and our man-made materials could not. So ultimately, I thought, well, if anything, our building skins of all things have to be more like the human skin. The human skin is the largest organ on the body, and the organ is supposed to protect the body before relying on the heart and the lungs, right? So in order to prevent overheating, it's the skin that's supposed to do that. And it does that by sweating or by raising goosebumps. It has hair, it's waterproof, it protects from disease, it does so many things. And so the idea is, why aren't our skins of buildings actually doing more than that? And why aren't we putting more money and funding into the development of it? So I started looking at what smart was, right? And how to make these smart things. And if you search it on the internet, this is what you get. You get a smart house. And the thing that makes it smart is mainly the gadgets that are attached to the building around. But if you look very carefully, nothing about the architecture is actually redesigned to be smart. The walls, the floors, the ceilings, they're basically the same, in this case, drywall or hardwood. And there's very little about the architecture that has adjusted to become part of that smart idea. I started looking at smart materials too, and thought that smart materials is a very good way to go because it does two things. One, it responds to changing conditions in their surroundings. So temperature, humidity, barometric pressure, light, all these different things, they can actually react. And more importantly, they require no energy and no controls to do so. So it's very, very different than smartphones, smart gadgets, all these things that are reliant on electricity. The smart materials are not. So the smart material that I work with is called a thermal bimetal. It's a lamination of two metals together, and they have different coefficients of expansion. They're laminated so that when the temperature rises, one side expands more than the other, and the result is a curl. So I use this curl for many different things, and you'll see as we go through. But in order to use that curl and some of the technology today, which is both computational as well as structural, I look a lot and gather a lot from geometry. This is another thing, part of my background that I have an inclination for, and you'll see that there's a strong sense of it, both in the small parts and how we tessellate the parts together into a tiling pattern, or how the overall structure is made in such a way so that it follows more like shell-like structures or minimalist surfaces. The combination of the original geometries now, again, with more complex geometries, the fact that we have computers or computation to be able to determine these shapes really helps a lot in my work. Okay, so there's the different parts of SMART that I use, the SMART geometries, the applications, the assembly systems, the assemblies and systems. And you'll see as I talk about them, these things are actually woven together and hard to separate whatsoever. So now I'm going to go back to this idea of moving targets and try to make a connection of these four different parts to my own work. What you'll find is that the four parts aren't very distinct, that there is overlap in all of them. But because these four things are very important, I think, in all of our lives right now, I want to point out that they are inextricable from my work as I work forward from it. So the first one I'm going to talk about is social justice. This is actually a very important aspect. I'm sure for you all it's the same. But in the US, we've gone through all kinds of different things recently with Black Lives Matter, Me Too movement, all these other things. I'm going to talk a little more about that as we move forward. We also have issues with the economy in terms of not only efficiency, but in cost and how we're going to look forward to that, mostly as a result of this pandemic. Climate and energy, as I pointed out before, is a very important part of what I think about at all times, and I'm sure you all do too. So you'll see that's a very big component in all of the work that I do. And the last thing is this idea of health and wellness, health being this right forefront problem of the pandemic, as well as something moving forward despite it, is this idea of wellness. And you'll see that in my work even before this pandemic. So I'm going to first talk about this idea of social justice. I know for you all, you're probably ahead of us. That's what we read in the newspaper all the time in New Zealand. You're like the model country. This idea of looking at pay equity, I think is really fascinating and fabulous. We are unfortunately very far from there. But this idea of social justice comes up quite a bit in many different ways. Recently, this past summer, this article came out in the New York Times. I don't know if anyone reads the New York Times there, but it was an article that talked about how, you can see here by the title, there's no reason for an architect to design a death chamber. It basically talked about how architects have a choice of types of projects that they choose, that they, instead of just being commissioned to do it, we have to really think about what we're doing. So this really struck a chord with me when I read it, and I thought, wow, you know what I mean? Architects must have a choice, and we're not so service to the industry that we'll take anything. Again, this includes everything from building possibly mega highways to nuclear power plants, to even border walls, which is a problem in our country. There are other articles too. There was a whole series that came as a result of the Me Too movement about women and how there are difficulties for women in our world. As architects, these also persist, right? So again, I can't speak for New Zealand, but in the US, when you go to any large event space, stadiums, performance halls, any convention halls, there are always lines outside the women's bathrooms. And why we don't obviously just increase the number of bathrooms for women than for men's bathroom, we don't know why. Women are always colder than men, especially in the workplace, but the standard temperature is actually set for men. And then things like the fact that women go through menopause and have hot flashes. And so now that you have temperature controls and temperature taking, depending on when you take it, women can be targeted also for problems like being identified for having coronavirus. So there are a lot of issues that as architects, we can really start to make change even in the smallest ways to what we do. But in my own work, a lot of these things come up because when I started looking at this thermal bimetal material, I wanted to find a material that was very affordable, that anybody could use, and that it wouldn't cost a tremendous amount for anyone or any application around this world. The thermal bimetal, keep in mind, has been in use for over 100 years. It's the typical thing that's a coil in a thermostat and is readily available. And so to me, that was actually a very important aspect of trying to find a material that was useful because, you know, you can use aerogel, which is a great and fantastic material, or all these other things, but they're so unaffordable that, again, how would we ever think that there could be equity in the use of it? So that was a very big deal for me. There are other things too. When I look at my work, I don't purposely think about how to design things that are feminine, but I think there's things that are identifiable to me, and maybe it's the way I see the world too, on even the naming of my project. So this was one of the first ones called Armored Corset. You can see the thermal bimetal is different here than the coil that is typically used, because for the first time, I propose using it as a surface material. The material I'll show you a little later comes on these narrow coils. So in order to make a surface, we have to make it out of a lot of small pieces, which is not atypical for architecture, and tile it in such a manner, or tessellate it is what we call it, that it then makes a very big smooth surface. So you can see here the basic pattern. The overlap you'll see with the other topics that I talk about is the idea of how this can perform. In this case, this was for ventilation. And so the idea was trying to make this taut surface when it's cold and make this very porous surface when it's hot. And by doing so, it will allow ventilation to freely go through. Again, trying to think of how solid surface can open up. So here you can see the tessellation from the inside. I also try to incorporate ideas about structure so I can eliminate structure. In this case, it's a completely catenary curve that's hung, and there's a whole tab, a groove and tab, no, it's a slot and tab type of system, right, of attaching the entire thing. We were able to put these things together very, very quickly, which is about this idea of efficiency too, and put an entire surface together in probably a matter of 4 or 5 hours. You can see here this idea of ventilation. On the left is cold and a little more taut, and on the right it starts to contort to allow air to move through in a more rough basket weave type of effect. This idea gets translated in many different ways. I'll show you projects that jump around in time because, again, there's no real sequence to how I show the work, but they all connect together by the fact that many of them are made out of thermal bimetal. So this was another one that I made. It's called Oculus. It has this inspiration from flowers, or the iris flowers that actually open and close, you can see here, but was the predecessor to, or not, I guess not really the predecessor, but along the same lines of what happens to this ventilating idea of how to open up things and ventilate. This next project was inspired by fish scales. Again, fish scales, animal scales have the ability to move not only with the animal as they move around, but also to perform in different ways. So in the case of the pangolin, which I showed you earlier, they're able to move their scales and open them up to flap so that their skin could ventilate and release hot air. And at the same time, it allows them to have protection from the things, an animal or danger around them. So in this project was the first one we did outside using the material, because I really wanted to get this into architecture and to respond to the environment. So I wanted to know how this material would react basically to the sun. Partnered with a few other people, including very innovative engineering, we were able to make this shell surface that was extremely lightweight. So lightweight that our biggest problem was uplift by far, rather than any kind of structural gravity load. You can see here, we clad the entire surface with the thermal bimetal. The idea was that it can actually shade when it's in certain formations, and it can also ventilate out the surface. So you can see that in the diagram here. We connected it at that time to Grasshopper. This is very early Grasshopper in 2011. I'm sure some of you might use that program, but it was unable to do a lot of things because it was so brand new that we worked with the company to develop their connection to software. So you can see here we were able to parameterize the tiles so that the tiles could be long and narrow or shorter and fat, depending on where it was in the model. We connected it with other analysis tools like Ecotech. Here's where the red parts, you can actually have exposure to the sun. The blue parts never saw the sun, so that way we can optimize the use of materials and be very efficient with that. The structural component is more like a monocoque structure, where it's reliant on both the surface as well as the minimized structural components. We had to design it because we build everything ourselves. We don't have any contractors come in to help us whatsoever. And so all these things were made out of small pieces, small from the tiles that made the squares, and we put the squares together. We connected it with structural analysis tools too, in order to optimize certain areas. So you can see the deep zigzagging that would help us more, or the thickening of the structure in different areas. Here you can see the day and the night view. In the night view, you can see how it's transparent on the right, because that area did not see the light of the sun during the day. And so we did not need any kind of operation on that. And so it's very lightweight. Whereas on the left side of the structure, the pieces are longer. And you can see in this next video, over the course of the day, how these pieces actually react. So in the morning, they're pretty flat. As the day goes on, they start to open up. They look like they're moving probably from the wind, but it's not. This is a time lapse through the entire day. And as you can see, the shade is going across it. They basically shut down again. So this was a very big thing for us, because we had no idea. If you stand and watch the thing, it really doesn't move at all, because the temperature basically stays the same. It has to be a temperature change throughout the day for us to understand it. So the next thing I'm going to talk about is the economy, the idea of economy or efficiency. It comes in different ways in my work. On one hand, it's this idea of cradle to cradle on manufacturing, being efficient and being thoughtful. Recycling, thermal bimetal is fully recyclable, although it requires carbon energy to make the material. The idea is to try to work as locally as possible and to be as efficient with it so that there's not a lot of waste. In this project, again, you'll see these are the pieces of the tiles from the last one. It's the Bloom project, where we had about 14,000 different pieces, and it was pretty daunting to have to do that. We didn't lose a lot of pieces, but we sorted them out the first day. And as we went to lunch and we came back, everything was all messed up again. So it was very distressing, because then we had to clean it up again. That I thought, wow, why can't I do a project using a single piece? Why do these projects always have to have so many pieces that I have to worry about losing them? And so this project was trying to find a way to make it out of one piece. You can see the material comes in a coil like this. And the idea behind it was, can we cut the coil in such a way and bind these together without using fasteners again, and make surfaces that way? And so again, it's a spiraling idea. if we spiral it and spiral it back, we can make this torus shape. And so here was our first attempt at doing that. And it was very promising because those pieces could also move when heated up and curl out and flare like the pangolin, but it can also start to take shape and form. So then we started developing it a little further, trying to see if we can add structure on the inside. If you look really carefully, there's a coiled structure on the inside to give it a little more firmness to the entire structure. And then we use all kinds of materials. I show these things to give you an idea of how we develop some of the products. Here we use a plastic so that we can see through and test it faster on laser cutting machines. And then we start to grow it further, right? We had difficulty with the last one because the structure was very hard to see and we're going cross-eyed. So we changed the color of the structure. We then upped the ante by making the structure go on the inside and the outside and the inside. So it was an interior-exterior type of structure system, as well as trying to figure out the pattern of connection for the clear torus portion. So you can see it developing here. We did yet another one. On the left, you can see there's actually two pieces. There's a structure that's all connected and put together, as well as the clear, which is coiled around the tube, and then how it's put together. And then the final, which we actually cut and made out of the thermal bimetal work. So there's a heating element inside there. The skeleton actually became the stand for it, and it became a portable display that could then be taken apart, packed in a very small box, shipped out, and put back together again. This idea of economy goes a little further into what is called cobotics. Cobotics is a word that's a combination of collaboration and robotics. So you get the cobotic, where the piece itself, in this case, when you assemble it, helps itself become assembled. So it's a combination of the effort of the person assembling it as well as the material itself. So it's a slightly different way of thinking how materials can actually be part of the assembly system. So the first proposal that I made was for the Museum of Contemporary Art in Los Angeles. And they commissioned me to make this pavilion that would actually sit in their space. It's actually, that was a really bad summer for them because they almost went bankrupt. And so we had to put that project on hold. But the nice thing is the Museum of Contemporary Art in Santa Barbara, California, picked up the project. And because I'm a researcher, I don't consider myself necessarily an artist, even though I like to do it. I thought of it as an opportunity to rethink the idea a little further. So in this case, to me at that time, I was thinking, well, structures came down to basically two things in architecture. It's either a column or it's a beam. It's either a tower or it's a bridge. And so if we're going to test this idea structurally, then why not choose one of them? And because of the space that they wanted us to put it in, it was more likely there was going to be a tower or something vertical. And so you can see here we took the same basic idea and put it into this tower situation. And what it is it, we're not forwarding. Now I'm stuck again. Okay, sorry. So what it is you can see the piece as it as we heat it up, and these are much thicker pieces than the previous project, so it has to curl at a much higher temperature. For us, it's about 250 to 300 degrees Fahrenheit. We put it in these ovens, they curl, we put it into position, and as they cool and start to flatten, we constrict them into a pre-stressed situation. What it makes is a very lightweight, very structured component. So you see on the left, this is a small model that we made, and it was already proving to be very, very strong and could stand up by itself, even though you see the pieces in tension, which is the plastic is very wobbly and thin. On the right is part of the real project that we put together. The colored pieces are aluminum, and we made them very thin and floppy so that we can again prove the fact that those things are actually held in tension, whereas the other pieces are in compression. So you see here the basic diagram. We heat the piece with a glove is all you need. One hand and one person is to put the piece into place, and as it cools, it flattens and becomes very strong. So you see here the video on the left, basically it needs one person to actually put the piece in, and the other person actually comes and gives the pieces. In the video on the right too, you'll see these aluminum pieces we put in first. They're very floppy, they have no shape to it. But as the bimetal pieces are being put in place, the whole thing takes shape and it becomes a more optimized structure, very, very taut and very strong. It was a very quick project to put together. It just took a few hours again. No fasteners involved. The thing that we didn't anticipate, again, I told you we build everything ourselves, is that we had to get the person in the middle out of the project afterward. And that was a whole separate design issue in the end. But we did get them out. So here you can see it. We built the bottom tier of what is to be a 5-tier tower. It was extremely strong. We worked with Arab Engineering. They tried to do an analysis of the structure on their computers at the time, and it basically crashed their system. So that the only way that we could test it was by the old-fashioned way of loading it with sandbags. But because this project was sponsored by the museum, they did not want to do that to what they consider artwork, what we considered research. So we never could test it, but it was estimated to be very, very strong. The next project uses the basic same idea, but here we're trying to look at how to make a bigger surface, right? The other one was this column, a tube-like surface, but how can we make a surface in itself? And the way that we considered it is, again, looking at biology, is these spheres, right? The sphere is great because it doesn't need an edge condition. It's basically a continuous surface. And so using that idea and some of the forms that you see here, extending it to looking at structures like Buckminster Fuller domes, how can we actually build our own things where we can look more at that surface? So took the same basic idea. You can see here in the colored pieces, that's the thermal bimetal. The gray pieces are aluminum or something else. When it's cold and blue, everything is flat. When we start to heat it up, it turns a little more, it doesn't really turn red in real life, but in this diagram, you can see it more in the kind of pinkish red. It's able to curl tightly. We put it into place. As it cools down, it starts to expand out again and is able to push all the pieces out in expanding positions. So when you put that into a sphere, basically it is all balanced perfectly so it's held together, again, using zero fasteners. So I go through these really quickly. We go through making a lot of different early ideas in paper. And then we move to plastics, other things here. Again, we had trouble seeing all the surfaces, so we use Sharpies and other colors to differentiate all the pieces. Then we move to other materials. Here is a smaller scale of the final model. This is about a 3-foot diameter model. All pieces that you see that are curved are thermal bimetal. Any flat or straight pieces are aluminum. So we're trying to make these systems that can be put together that are very strong as surfaces by using the combination of that compression tension idea. And then finally a third model here before we try to move forward on what we wanted to build. Before we do that, though, we always have other ideas that we step backwards into. And here again is an assembly idea of how to thin out the materials, make them longer, thinner, overlapping, woven. And finally, what we did was we ended up starting to put these things together, selecting it, and choosing one that was actually buildable for us. So what you'll see here in the end, this was the surface that we ended up building is about a 9-foot diameter sphere. All the petals that you can see, especially in the different blue colors, have no fasteners again, but are curled in those ways or formed in those ways so that they hook together. A lot of people think, wow, it's like this, like so beautiful. It's so flower-like, or people recognize it as being very feminine looking or very ornamental. But none of the all the ornament in all our projects are completely functional. There's reasons for them and there's purposes for them. So we built this for the Los Angeles Municipal Art Gallery at first. But because it was there for a short time, we then decided to take it to the South Coast Botanical Garden in Los Angeles. You can see us rebuilding it here in a time-lapse image. The thing structurally, you see it gets really floppy and almost like collapses until we put that last piece in. And when we put that last piece in, it then stiffens up beautifully and you can just roll it around almost anywhere. So here it is in the South Coast Botanical Garden. I really like the position of it as well as it being there because their attitude to art is a little different. Like the garden, it is always changing. The plants are growing bigger or smaller or dying or moving. And so they've allowed us to change the piece over time and to continuously test things on it so that it's an artwork that actually evolves as opposed to something that is static and stays the same. This has led to other type of work that we do. This is what we call the self-assembly studies, where basically now we've eliminated the human whatsoever. It's no longer a one person, one hand operation. It is no person, no hand. And so these are very small things that we did initially that then grew into other larger type of projects like you see here. This probably is about a 3 or 4 inch diameter sphere that we're able to make. It's supposed to be actually a wheel to a or flat packing vehicle that's self-propelling. Here are part of this idea of propelling. We also design these solar turbines that now can generate energy. And so they basically can go on infinitely. They're not obviously as efficient to generate a lot of energy right now, but they still can generate energy, which is a very big deal for us again. So I'm going to talk a little bit now about climate and energy. It's not that I haven't been talking about that. A lot of the other projects you can see do address those things of climate and energy. But this project actually does so in a very direct way. It's probably of all the projects the most ready for commercial use. We are actually piloting right now, and I'm going to show you some of that in a second. But here's the problem, at least in the US. Buildings basically use a lot of energy. This is actually an older statistic from 2012. 47.6% of all energy is used on buildings, more than transportation of industry. And of that, a lot of it is used on HVAC or heating, ventilating, air conditioning. Those numbers have improved over time. Here's 2019, but still, buildings are still more than the other two. And we're still trying to find ways to reduce that. The other problem that I'm sure you all have heard about at least is this heat island effect. Basically, there's too much concrete and too many hard surfaces in cities so that they're not able to cool down at night to start a cycle, a daily cycle. It's exacerbated by this problem with air conditioning that I show here. So as the temperatures rise, people start to use air conditioning, and they use more air conditioning. In order for air conditioning to operate and cool the interior of a building, it has to give off hot air into the environment. So basically what it does is it's also heating the environment in addition to not allowing it to cool down. Here's a US statistic that is really quite alarming too if you think about it. 9% of all US energy in 2018 was used on air conditioning, 9%. 12% of the total commercial sector electricity consumption was used on air conditioning. This is just air conditioning alone. This is mostly clearly on commercial buildings mainly, and a little on residential. But you got to think, wow, what are we doing? Again, I look at some biological references and inspiration. Here you can see the nest of social weaver birds. They're very resourceful. They build on anything, including telephone poles now, and they build in communities, right? And so you can see the entry holes on the bottom of this nest where the birds will come into. They take different positions in the nest depending on what temperature or humidity they need. So in the very center is highly insulated, and out on the edges, right, it can actually get cooler at night in the desert-like atmosphere. And so depending on where they need, they actually can move around inside this nest for what temperature they need. The termite mounds also are very smart. The termite mounds basically have an entire system of pathways where whether they want to allow the place to ventilate and have all the openings unplugged, will cool the place down. And if not, and they need to warm it up, they will actually plug up some of these holes to then seal the air inside. It's a very, very simple, very smart system. So trying to think about some of these smarter ways to operate. Again, I talked earlier about the building envelope. It's using and trying to deal with areas where we have big problems. One of them is in the window system of buildings. So here's the typical problem. Everybody wants floor to ceiling, 360-degree views, right? But the problem actually is no matter how much you condition that space, the sunny part of it is still going to be warmer than the shady part of it. And by doing so, you still have to be pumping a lot of air conditioning to do that. So you see that also on the right side when the windows have no coating or nothing on it. Basically, you get a lot of heat gain through those windows. And low E coating, which works great, is very affordable, is becoming problematic to wellness because the reality is it's like wearing dark sunglasses indoors all the time. It's now in studies being very poor for wellness. And we have to really rethink how we spend our time indoors with those coatings. Electrochromic glass too, although it seems like it be dynamic when it actually shuts down, in some cases has a color tone to it. In other cases, it's completely cutting out all visibility whatsoever in order to cut out the sun. Blinds are a problem that helps with glare, but the blinds still allow that solar heat gain to come through into the windows. And then obviously when you use these blinds and you have to shut it down, you lose a lot of visibility. So this product that I invented using the thermal bimetal, we put it inside the cavity of a standard IGEO or a double glazed unit. Basically, it reacts to the sun. They close, they flip over, as you can see, to block the sun. The great thing is when it's basically in open or closed position, the visibility is completely the same. So you do not lose any visibility when it's actually shading. The system that I use for the thermal bimetal is a toggling system. I told you that there's a curvature to it when it heats up. We actually reverse curl it so that when it's cold, it's in one configuration. And when you heat it up, it reverses and then is able to flip over. So here you can see a close-up of it. They can actually flip independently, individually. So they don't all flip together at the same time, but probably within about 10 minutes of the entire system. So they're very beautiful. A lot of people connect them to being very natural-like or almost like butterflies inside the window. Here you can see it in a time lapse over the course of a day as the sun comes in and hits the surfaces, they start to flip over. And during this daytime, it'll, as long as it's sunny, will stay in its operational shading position. And then at the end of the day, as the sun leaves and you get more shade, you basically get more light coming in. Here you can see the different configurations. The facade or the building can change throughout the day, depending on how many pieces are open or closed. This is actually a view in the wintertime. So because it's cold outside and the sun is not at its strongest, it will allow the heat to come in and to passively heat the interior. You can see they're not flipping over. And this is the summertime. You'll see it flip over at a certain position and shade the interior. And they will react to the sun, stay closed until the very end of day. But the nice thing that you see in this imagery is that the view or visibility outside basically stays the same whether it's open or it's closed. We've gone through different kind of testing and certification. So you can see here at one of the certification centers in the United States, we actually went up to test our windows and got some really great results out of it. We have a lot of awards this past year because now we're at the point where we're piloting it currently, and then early next year, we are going to start putting it in for early adopters. So this is the pilot that's actually going in tomorrow. It's going to be at an architect's office in the Los Angeles area. And then in a couple weeks, we're actually putting it on the Cal State Long Beach campus. We're using a container to put it in so that we can use it as a real-life testing center. You can see it here in the making. Long Beach is also one of the largest shipping ports in the world. And so shipping containers are pretty readily available there. And so we're also recycling some of those shipping containers to do this. We're partnering with an artist named Yalu and to basically clad the entire shipping container itself with the artwork with the vinyl wrap. You see here the 4 windows on the front are going to be the invert system that I just showed you. Because we have all these pieces and we're able to color them, we can actually pixelate the imagery so that you can see here, we took some of the artwork to actually run through the window. So on the outside, it has this kind of opacity to it because of that, but on the inside, looks the same way as you've seen before, that you can actually keep the visibility when open and when closed. The container is not inhabitable except for testing, and so we put these windows on the back that you can look through and see the system. These are other little things that we are working on. This is a ventilator, a common ventilator on the roof. I'm sure you have those too. The great thing is they just catch the wind and pull and draw air out of the building. But the problem is in the wintertime for us, it can get cold, and it'll allow the cold air to also go in and down into the shaft. So to prevent that, we were trying to design a similar thing that would actually close down when it's cold and basically open up. So here's one of our very early prototypes of how to get that done. And then obviously when it cools down, these pieces flatten out again and prevent air and cold air from going down into the shaft. Okay, so the last thing I'm going to talk about is this idea of health and wellness. It's something that I'm very much consumed with, not only recently because of the pandemic, but for a couple years before that. If you start to look at how architecture basically correlates with the food industry a little, on a very, very basic level, historically, right? So long ago, food was used for fuel. And then, as the cultures became richer and the economies start to develop and things like that, food became something that was more of, for gluttony, just the more of it that you had, the richer you were somehow. And then more recently, there's this idea of food for nutrition, right? So everyone's now trying to eat healthy, this idea of organic, all these different kinds of diets that we can go on and on listing forever. But this interest in eating food for health was really important. Again, architecture long ago, was basically just shelter. Any way we can get shelter and try to do it as smartly as possible for insulation, for protection, for all different kinds of things. Then there's a period that architecture is for luxury. We still, I guess, have a little bit of that. But again, the opulence and the ability and the strength and the power and the expression of it was something that was very important. But more recently, as we all know, there's this idea of architecture for wellness, right? What is wellness, not only for the human being, but wellness for the planet? And so part of the research that I'm working on now with a big team of people is this idea of dealing with air pollution. And the way that we look at it is that architecture in the city basically has all this surface area. I talked earlier about this idea of heat island effect and the hard surfaces that we worry about, and how a lot of that hard surface needs to change, the highways, the sidewalks, etc. But what I proposed to the Society of Engineers, or the National Academy of Engineers a few years back, is why can't we be using architecture surfaces on the outside for infrastructure for the city? Why aren't these surfaces basically being used for the good of the public as opposed to the interior occupant or for the developer? So typically it's used for branding. We try to make it look pretty as a building. And at best, as a performance criteria, we can actually use it to filter things to the inside, even as I showed you the invert windows or for ventilating and all those things. But my new thing is, why can't we use this for the outside, for the pedestrians, for the people who are on the outside who are not inside the building? So in the case of urban canyons and smog, most of the particulate matter actually sits at this lowest level, which I call zone 1 at the bottom. The mid-level, zone 2, the highest level are where we don't have to worry because pedestrians aren't there typically. And it also is much less smoggy in those zones. So it's in that lowest area that becomes the biggest problem. So the idea that I have first is trying to, in a very passive way, filter air so that building facades can actually be a filtration surface for the city to eliminate smog. There's two levels of it. There's both the particulate matter as well as gaseous smog. And so the idea is, again, using Bernoulli's effect, using prevailing winds, using chimney effect, try to move air as fast as we can through the surfaces, through the pores, so that we can filter both of those things. And the filtration happens not only with an actual filter for particulate matter, but the inclusion of materials like titanium dioxide into the surface so that we can also deal with the gaseous matter. So here we are. This is ongoing research. We're not at any product quite yet. Again, you can see a lot of the work that I have are very basic science level all the way to commercialized products. But in this case, we're actually working on it. I just want to show you the stuff because I'm excited about it. We build our own wind tunnels. Here you can see a preliminary tube on the top that you can see in a very clear resin 3D print that we built. It's sitting inside its wind tunnel tube. On the bottom, you can see some of our simulation models showing how it actually moves through the surface and the air moves across. Eventually, we're going to get to the point where we can tessellate the surface with all these different tubes in it so that the air can actually move in and out of these holes. We still don't know what scale or size these tubes will be because we're just trying to control the air and how to get the maximum amount of air in it. So again, these tubes could be, I don't know, 20 feet long, or they can also be half-inch long. We don't know quite yet. And then what we want to do, which is probably about, again, going to the social equity and climate and all these things, is to design these bus shelters that could be anywhere in this world. So these bus shelters can actually be 3D printed. We're working on how to use dirt, local dirt, to be able to put into these 3D printers so that they could be 3D printed anywhere and assembled and work passively so that there's no energy that's required and that everything is low cost and there's no issue with theft or other things like that. And the idea is basically give the freshest pocket of air to the people who sit there and wait for buses. And that way we then bring equity to everybody. The final little project I'm going to show you here is in the area of robotics. You can see here we can make these things not only self-assembly, but we now can do things that are self-propelling. And so even though they're very, very low tech and very, very simple, they bring a lot of things to the forefront. And so when we started making these little critters, we realized they make us smile or they make us laugh, and we actually give them names, and we have our favorites, and you know what I mean? And we start to feel really connected to these pieces. And so by doing so, basically, at first I thought, well, how is this going to ever affect architecture, right? I mean, we're not going to make architecture walk, you know what I mean, when we're this basic. But we can make architecture move on the surface. And so when we start to do that, it made me really think of, does architecture actually have implications to the public too? Can we actually love our building, or does it have some emotional value that's going to evoke from us? And so this project came out of that and made me really think about another level of what we can do for architecture and how we can use architecture for mental health. And so this idea is in its very early stages. And propose on getting funding for now. If we can actually make a facade change and move, and if we can actually have some emotional attachment to it, then what if we can make it smile, basically? And so if we can actually find the gesture of smiling just as a contortion on a surface, and if people can smile back, if one person can smile back, if 10 people, if 1,000 people can smile that day, basically through studies, when you smile, you've improved your own happiness, your endorphins come out, and therefore we can possibly raise the level of mental health in a city. And so these ideas are, again, toying with the art, with the biology, with the movement, with wellness, all these types of things, and trying to figure out how to contort it and how we can move throughout the day and think about how architecture can really impact public health. So I'm just going to end on these last few images, which I think are really significant to me. It's from an artist, Richard Barnes, who really speaks to me when I see it. It's on one hand disturbing, on the other hand really quite interesting. The combination again of climate, of artifacts, of things that are alive, things that are not alive, what is right, what is wrong, all these different elements in the work, museums. What are we doing? These questions that I ask myself over and over again, and end with this image of a flayed man. And flayed, I actually, long ago had to look up what that meant. Basically, it is removing the skin or the skinless man, going back to this idea of how skin and a building and humans and stuff all basically interconnect in my work. And the fact that this flayed man is leading these skeletal biological remnants in a piece of architecture was really significant to me. So I will leave you with that, and thank you very much. That's my lecture.
Thank you very much, Doris. As I said before, if anyone's got any questions, please put your hand up and Brent can get a microphone to you. If you do have a question, please look into the camera here so Doris can see you. So, anyone got any questions in the audience? I wouldn't mind starting off by just probably a very obvious question, Doris, is how do you scale up all this great work you've been doing, and how do you find people that are going to produce the work at some large commercial scale so that we might eventually see it on the facade of a building tower, for example, in Los Angeles?
So the invert window system is our closest to doing that. I showed you that we're actually piloting right now. In the spring, we have a few installations that are probably about, I'd say, 1,000 square feet. And we plan to make it grow. We have a lot of interest and inquiries from larger firms because they want to put it on about 200,000 square feet. I don't think we're really quite there yet because the idea is to try to grow it slowly, because I think in architecture we have to have not only safety, but warranty, all these different things settled for people to really feel comfortable with it. But hopefully within probably the next year or two, it'll be available on the market, possibly anywhere. I think the other facet to that is in the construction of that, I don't know, I learned that the IGU, or the insulated glass unit, the standard double glazed unit used for commercial applications, is a very fractured industry, at least in the United States. So there's no single large provider of those types of window units. They're very localized. There's probably about 4,000 providers in the US. The good thing with that is that they can actually build very locally. And so they order the glass from the big glass companies, the films, and then they actually build the IGUs locally. So the good thing for us is that if we provide our inserts into that glass unit, we can actually then ship it, which is very, very lightweight, to those locations. They could assemble it local to the construction and therefore reduce the amount of footprint. The same thing can be done internationally because we've designed the system so that we have different areas that we can stamp out the product, assemble it, as well as deliver it to local manufacturers of the window units. So it's again part of that cradle to cradle, economy, scaling up, sustainability, recycling, life cycle, all these things that we think about and talk about as a major part of what we do.
Can I just ask something else? How do you do all the things you're doing? I mean, how do you combine teaching and this work and your other architecture work? That's one issue. And how are you managing to do it this year in Los Angeles?
Well, okay, so you all know that we in Los Angeles, in California, the U.S. It's different in different areas of the U.S. In California, we are about to go into a stricter shutdown tomorrow, where they're actually closing all outdoor eating and dining establishments even. Masks are required everywhere. I have not been to the university, to my office at the university since March, and have been working remotely in my studio. So it's not been good here, and things have changed a lot. Thank goodness for Zoom and for video calling like we're doing now, because I think without that, I would not have been able to carry on. And the thing that's lucky for us too, in the state of California, despite the shutdowns, manufacturing, as well as the architecture, construction industry has been considered essential. And so architecture, building, construction, all these things could continue. So for good or bad, we're able to still build and work on the things that we need to. But it's a little more difficult because we can't just drive anywhere and just talk to anyone and build anywhere. Everything has all this new protocol to it. Balancing with, with teaching and administration and my appointment at the university, as well as family and my firm is not an easy thing. A lot of people ask me about that, and I guess if I really stop to think about it, it's not easy. But I guess in the conditions now, in some ways it's a little easier because now I don't have to commute. In Los Angeles, typically we all commute and we spend a couple hours on the road every day, moving around. So that saves me a little time by not having to commute and to deal with other stuff. But I don't know. I think I just do it just, without thinking, just in order to get it done. I also think though, as an architect, I think a lot of the architects out there probably would agree. The beautiful thing with being an architect is that we're all very resourceful in how we think, right? In detailing and designing. And we think in terms of scenarios or in options or in alternatives. And if you're really not biased thinking that, oh, there's only one way to do it, then you can always find ways to get things done. And so I think to do my work, that's the same way. It's like, okay, if I can't do it the other way that I typically do it, what other way can I get it done? And so you think in terms of being resourceful, and it's got to get done somehow. And so you do it. So I hope that answered your question.
Yeah, I think it does. I have one more question. It's just you seem very atypical in the way you approach architecture, and that most architects, the traditional model has been quite passive. An architect waits for someone to come in the door or get on the phone and bring a job to the person, but you're actually being much more active and getting in there and finding a solution, then trying to bring it to market, which is unusual for an architect, and I think disruptive of the way architects traditionally behave in a good way. So is that something a path you've been determined to go down?
Yeah, I think so. About 15 years ago, I think I told you I was, for many years, for probably 15 years before that, I was practicing as an architect. And I got very frustrated because I couldn't understand why, as I kept moving forward, I kept thinking, oh, there's going to be all these like great products on the market, and architects are going to change. You look at the vehicle industry, and as they went from just guzzling vehicles to all the, to hybrids, to now electric cars, to all these different things of performance and how, they've changed. I thought, wow, architecture, well, is obviously going to do that too. But then got very frustrated because I realized it's like, well, it's not really happening as fast as I think it should be. What is the problem here? And where are these products? And so as I started looking deeper and started looking further, trying to find these things, I realized I can't find anything. And so decided that I would jump into it myself. And it's like, okay, well, if no one else is going to do it, then I'm going to just have to go design these things, because it was, frustrating in my mind to just be an architect who's limited by things that you can specify. So spent more time trying to find those products, look for these things, and change the way we look at architecture. But I think I actually think it's a model, now that I've come this far, not that I intended it to be this way, that we as architects should really think a little more about, right? Not very many architects are involved with research or determining products out there. Mostly engineers, mostly industrial designers. And why not architects if we're the ones who are actually specifying it? And what it does too is instead of turning on its head the fact that architects are just service to the industry, instead of us waiting for the customer or the client to show up, why can't we turn around and control the supply part of it, right? So that we actually supply and provide the products instead of be the demand end of what's out there. So I hope that more people would want to think like that and change how architecture is so that we can keep up with some of these other industries.
Hi, Doris. I'm really excited about your work. I actually did a project when I was studying architecture in the year 2000 about how the technology of architecture was so far behind the technology of anything else. The particular project I did was on ski clothing technology and how that was so much more advanced, and could we use those same principles in architecture? And I'm even more excited to see the principles applied effectively through the inspiration of nature. Also really excited about the potential for design for deconstruction and how you can take the modular pieces that your structures are made from and then reuse them elsewhere. One very basic question, in particular related to my movement since then into life cycle analysis, have you considered what happens to be able to recycle the bimetal because it's combined? What's the recycling potential?
It's fully recyclable. From what I understand, it's a temperature thing, so that when they go to melt the material again, it actually divides or separates, so that they're able to then capture the material and identify the different alloys of that.
I've just got a question for you too, Doris. There's probably a few facilities managers in the audience who, I guess, would inherit these materials and have the responsibility for ongoing maintenance of them and cleaning, etc. What work has been done in terms of understanding the biometals' life, longevity, and the thought around ongoing maintenance levels for these biometals?
It'll last a long time. It depends how it's treated, just like any metal. If you just lay it outside raw, probably will last about 7 to 10 years. On an interior condition, not outside, they will guarantee that it'll last 40 years. Inside the cavity of the window where we put it, it basically will last over 100 years because it's a sealed environment. But it's just like anything. To keep it outside longer, for example, as a raw material, you just treat it. You treat it with either oils or you treat it with painting or priming, you know what I mean, primer. But it's just like any metal.
Hello, thank you for your very interesting, mind-blowing talk. I have a question about materials that are designed to respond to wind or rain, because in New Zealand we spend a lot of time thinking about how to keep our buildings warm, how to prevent, you know, water from getting in and staying inside buildings. So I'm just wondering if you've done any work with materials that are designed to respond to water and drying, that sort of thing, rather than heat.
Yeah, no, that actually is a good question. I actually have not, but I do know there are things out there. There's the institute in Germany at the University of Stuttgart. They do a very similar type of research to what I do, but using wood veneer and wood laminate relative to humidity. So as the humidity goes up, or if it rains, or if things are waterlogged, they actually react in different ways. That doesn't necessarily address your problem with controlling the cold air from coming in, but that's something about humidity. It's you know, I think what you bring up too is something that I would like to point out to everybody. There's actually so much research to be done in this area, and so few people. I have so few colleagues and peers that work in this area, but really, it's just a tremendous area. You know, in what you're saying, in areas of insulation and thinking about using other types of smart materials. There's thousands of different smart materials out there. And thermoenvironmental is not the only one. I happen to work a lot in it because every time I finish a project or we're in the middle of a project, we think of something else to do with it. And instead of, you know, I mean, jumping onto another material, we think it's like, well, because we have all this expertise in it, plus all this equipment and ability to work with it, why not, you know, keep, you know, working forward? But it's not because we have no interest in other materials. We just don't even have the time to actually move on quite yet.
Hey, Doris, I think we're going to release you now. Thank you so much for your time. It's been a pleasure meeting you, talking with you.
Thank you.
Thanks for your presentation. And I'm sure we all hope things improve for you in Los Angeles and California in the next year. And so good luck with everything.
Thank you. Let's hope.
Yeah, and we'll all follow your career, I'm sure, with interest. Thank you very much, Doris.
Thank you very much. Have a great day and a great convention. Bye-bye.
cool. Yes, it is.
One, two, three, four, five, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Check test. 1, 2, 3, 4, 5. 1, 2. Check. Test. 1, 2. Yeah. Ha ha. 2, 2. Yeah, yeah. Test, test, test. 1, 2. 1, 2. 2, 2. 2, 2. Yeah, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Ha ha. 2, 2. Yeah, yeah, yeah. 2, 2. Yeah, yeah. Ha ha.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7,
Is it okay? Is it okay?
Technology challenges. Or is it a cable?
I think it's just that one. It's like struggling. So it's gone again. I will attempt to make my work. The other end.
Cool. And pick up.
Kia ora koutou. Welcome along to the Bunnings Trade Speaker Series. Today we have Ulrich Fruick, the founder and director of Adroit. He's exhibited with us a number of years at the show. And today he's discussing IoT is awesome, so why are the odds your project will fail?